In the previous episode of Space Science, we talked about the Coriolis acceleration present in a rotating space station and how it affected the motion of objects in it. Remember that in the last part of the video, I showed you some simulations of boxes being knocked down by a projectile shot from somewhere in the station. In this video, I will teach you the mathematics of how to compute a targeting solution in a rotating frame using various assumptions. Let's just jump into it. Like seen previously, things are much easier to deal with in the inertial frame. In order to hit the target with a projectile, we need to understand how it moves. Remember Newton's second law of classical mechanics? Force equals mass times acceleration? Because of that, the projectile goes in a straight line at constant speed. So, in order to hit the target, it's super easy. We only need to aim directly at it. Oh well, I might have forgotten the fact that the target itself is moving, and by the time the projectile has reached where it was at the moment of the launch, it has moved and is now somewhere else. So if we want to hit the target, we need to be able to predict where it is going to be after some time delta t. Considering that the target is static in the rotating frame, it follows a uniform circular trajectory in inertial frame. Since the angular velocity omega is constant in this case, the angle of the frame for any time t is simply theta equals omega times t. Using the typical direction cosine matrix or rotation matrix, we can transform the position of the target from the rotating frame to the inertial frame. Let's clarify the notations here. Everything with the subscript I is expressed in inertial frame, while the subscript r designates the rotating frame. Also, we will call A the initial point from which the projectile is launched, B the target, and P the position of the projectile. Before we can keep going, we need to arbitrarily decide of a time of flight, delta t. Now that we know exactly where the target will be in time, we can compute a direction vector, point B minus point A, both in inertial frame. But since we throw the ball at t equals 0, point A in the inertial frame is equal to point A in the rotating frame, because theta at t equals 0 is 0. The rotation matrix degenerates to the identity matrix, which is a nice simplification. For now, the direction vector has a non-unit length. In fact, its length is exactly the distance between A at t equals 0 and B at t equals delta t. We will save it for later and call it d. Since we know the velocity will be constant, we can use the simple formula distance equals velocity times time rearranged like so. Velocity equals distance over time to compute the velocity required to reach the target at exactly t equals delta t. The full equation of motion of the projectile is therefore what you can see now. The position of the projectile is computed from its initial position plus the direction vector normalized, that means that its length is 1, multiplied by the initial velocity and the time. Using this technique to solve for 3 trajectories with a time of flight of 5, 10, and 15 seconds, we obtain the following results. And that's about the easiest way to solve this problem. But wait, we're not going to stop there. Imagine now that instead of a constraint on the time of flight, we have a constraint on the initial velocity expressed in the inertial frame. The new method starts almost the same way. We choose an initial velocity and a candidate delta t. That means that we treat it as a variable and not as a constant. In other terms, we allow it to change, and we will actually solve for it, that is, finding its best possible value. Visually, varying the value of delta t while keeping the initial velocity constant looks like this. The position of the projectile is computed using the same equation as the one we saw before. With every value of delta t, the direction vector is different, and the position of the projectile along its trajectory is proportional to delta t. We can see that in this configuration, there is only one solution, one unique value of delta t that will result in the projectile hitting the target. In the general case, however, there might be more than one solution. So, as you already understood, if we want to hit the target, we will need to optimize the value of delta t. At the heart of any optimization problem is the objective function. Without it, it would be impossible to optimize anything. The objective function, like its name suggests, is used to define mathematically the objective that we have in mind. In this case, the objective formulated in plain English is find the time of flight necessary so that the projectile hits the target. If we refine it, we obtain the following description, more accurate. Find the time of flight necessary so that the distance between the projectile and the target is 0. And now it's just a matter of converting this spoken language statement into a mathematical one. Let's do it step by step. The time of flight is delta t. The distance is going to be written as the norm of the vector going from P to B at t equals delta t. The value of P can be computed from the equation of motion, and the value of B can be computed using the rotation matrix. Combining everything, we get the following objective function, which is in reality an equation that we want to solve for 0. Now, because it is easier to understand what this function does when we can see it, let's replay the last simulation and juxtapose the graph of the objective function. As you can see, when the projectile hits the target on the left, the function dips to 0 on the right. That's where our solution is. Now, you may wonder if it would not be better to use the square of the norm in the objective function in order to get a smoother minimum to find. And in the general case, we would want to do this for mainly 2 reasons. The first one is that because of the square in the function, the minima are going to be smooth, because the objective function is going to be differentiable everywhere. Many minimization algorithms prefer or even require the first and even sometimes the second derivative to be continuous at the minimum. The second one is more mundane. By taking the square of the norm, we actually save ourselves the computation of the square root, which, when evaluated many times, could slow the entire process quite a bit. However, in our case, we will keep the square root, and I will explain to you in a minute the reason why. Let's take another look at our objective function. It has a lot of transcendental functions, like the sine, the cosine, the square root, and unfortunately, we can't solve it by applying the traditional techniques that we learned in high school. One very simple example of a problematic transcendental function is this one, x minus 1/2 of sine of x. As simple as it seems to be, it is impossible to find a closed-form solution for it, and approximations have to be made. Fortunately, we approach the problem as engineers, not mathematicians, so we can be satisfied with only a decent approximation of the real solution. Now, there are many ways to solve this equation in an approximate way, and scientists have been developing specialized algorithms for hundreds of years. Today, we're going to use one simple yet very powerful algorithm called Newton's method. This guy again. Newton's law, Newton's method, he's everywhere. His method revolves around a simple concept called linearization. Linearization is a very common simplification process in science and engineering. It drastically reduces the complexity of a problem at the expense of precision. Instead of using the objective function that we derived earlier, let's take this simpler function as an example. Absolute value of cosine of x. It has the same kind of shape but has a much simpler analytical formula. We can also solve for its roots exactly, so we can check that the algorithm works the way it should. The algorithm is iterative. That means that it needs a starting point, an initial guess. The closer the guess is to the real solution, which in the general case is unknown, the faster and more reliable the algorithm will be. Starting at this initial guess, we trace the tangent line to the curve and will consider that the function can be represented by the straight line. Now, it is obvious that it is not such a good approximation of our nonlinear function, but it has a huge advantage of being extremely simple. Because we're trying to find a root of the function, that is a point where its value is 0, we can easily compute the intersection of the line with the x-axis. As you can see, the intersection between the tangent line and the axis of abscissa is much closer to the actual solution than the previous point, which was our initial guess. All we have to do now is to repeat the operation until we judge that we are sufficiently close to 0. And that is Newton's method in a nutshell. Very simple, yet very powerful. Now, mathematically, it uses the first derivative of the function in order to approximate it. it is necessary to be able to compute it one way or another for the method to work. The next guess of the solution is computed using the following recurrence formula. One problem that is evident with this method happens when the derivative, that is the local angle of the curve, becomes too small. Indeed, because we are tracing the tangent line, if the derivative is close to zero, the tangent will be close to the horizontal, and the intersection with the axis of abscissas will be really far away, and possibly at infinity if the derivative happens to be exactly zero. Now, imagine that instead of this sharp change in direction around the solution, we have a smooth basin. Nun's method is actually not going to perform well in this sort of scenario, leading to a lot more iterations and, by extension, more function evaluations and more work overall. That's why we decide to keep the square root in the objective function, because the convergence will be much faster. Let's go back to our original optimization problem. In order to find a solution, we need to give an initial guess to the algorithm. Thankfully, by analyzing the geometry of the problem, we can determine the interval in which the solutions are contained. Indeed, because we know the velocity of the projectile and we know it is constant, we can compute the time of flight based on the distance. All we need to know is what the minimum and maximum distances are. Since the trajectory of the target is a circle in the inertial frame, the closest point will be at the same angular position as the initial point. Similarly, the furthest point will be on the opposite side. This gives us two times that encapsulate all the solutions. Conceptually speaking, what happens is that the projectile cannot hit the target before it has traveled at least the minimum distance separating the initial point and the target, and it cannot hit the target after it has traveled the maximum distance between the initial point and the target because it keeps going in a straight line. It cannot go backwards, so there cannot be any solutions there. Let's take another example with multiple solutions to really visualize what's going on. The initial velocity of the projectile is kept constant but is relatively low. As you can see, we hit the first solution just after the lower bound, and we hit another one in the middle, and the last one just before the upper bound. Now, as a general rule, we want to reach the target in minimum time, so the initial point we give to Newton's method is the lower bound. Let's complicate things a bit. Until now, we have considered that there were no perturbations such as gravity, magnetic interactions, solar radiation pressure, nor aerodynamic drag. However, if we want people to be able to live in the station for more than 30 seconds, they will need to be able to breathe. It is therefore likely that it would be pressurized. That means that there would be an atmosphere within the station. For simplicity, we will consider that the atmosphere of the station has uniform pressure and temperature and that it is static in inertial frame. This is crucial for the rest of the computations. The equation of aerodynamic drag is generally the following. The drag force is equal to 1/2 of rho times v squared times s ref times cx. Rho is the density of the fluid in kilograms per cubic meter. S ref is the reference surface of the object in square meters. V is the velocity of the object with respect to the atmosphere in meters per second, and Cx is the adimensional drag coefficient. Since this equation describes the drag force, we need to divide it by the mass of the object to obtain the acceleration due to the drag. Now, it's not very practical to work with all these terms, because in this case, they're all constant. We therefore find them, bring them all, and in the darkness, bind them. Sorry, what was I saying? Yes, we're going to fuse all these terms into one, Cb, the ballistic coefficient. So, what does the presence of drag change? It changes the way the projectile moves. More specifically, it changes its velocity through time. Let's derive this step by step. As you already know from your high school physics class, the acceleration is the time derivative of the velocity. Replacing a by v prime, it becomes obvious that this is no ordinary algebraic equation. Because we have stuff that depends on its derivatives, the equation is a differential equation. There are many ways to solve a differential equation, but unfortunately, very few of them actually have a closed-form solution. That is, a solution that we can write explicitly in a mathematical formula. But, thankfully, in our case, this differential equation has one. Now, because I'm a lazy engineer and not a mathematician, I'll just ask Mathematica to solve it for me. And that's the solution it gave me. We can see that there is a term that wasn't there before, C1. That's the integration constant. In order to figure out what it actually is, we need to use what is called a boundary condition. In our case, the boundary condition is that the velocity at t equals 0 is v0. Solving this equation for c1 gives us a value of -1 over v0. Injecting this result in the formula for the velocity as a function of time, we get its ultimate form! Yay! How does it help us, you ask? Be patient, I'm getting there. Remember that in the algorithm that we derived earlier, we need to compute the position of the projectile at any given time. In the previous case, the velocity was constant, so computing the position was trivial. Distance was equal to velocity times the time. In the case with aerodynamic drag, however, the velocity is not constant anymore. We therefore need to integrate it with respect to time in order to get the formula for the position as a function of time. Once again, the unspoken rules of laziness force me to delegate the boring work to a machine. And this is what it spitted out. We are now ready to solve the targeting problem in a rotating reference frame in the presence of aerodynamic drag. Using what we just derived, we can finally build the new objective function. We simply need to replace the distance from the origin from v0 times delta t to our nonlinear function of delta t. And voila! Here you can see the trajectories of 3 baseballs thrown from the same point with 3 different initial velocities, 50, 100, and 150 meters per second. We observe that although the velocities of the projectiles are relatively high at the beginning, they slow down extremely quickly, but they never quite stop moving. And finally, for those who made it until the end of this video, you can see how the presence of aerodynamic drag changes things. The blue curve is without drag, and the pink one is with drag. It really does change everything. And this brings us to the conclusion of this video. We have learned that it is always good to try to simplify the problem as much as possible before attempting to solve it. Usually, it is possible to do so by changing our perspective on things. We also have learned how to numerically find the root of a nonlinear function using Newton's method. And finally, we have learned how to incorporate the aerodynamic drag into our problem in order to make it more realistic. Remember that the techniques shown in this video can actually be used to solve a wide variety of problems, not just the one we took as an example. And that's all for today. I hope that you learned something useful. Don't forget to leave a like and subscribe for more videos like this one. Peace!